Okay, we've got two different containers that's holding a fluid, and the fluid is the same in both. And we fill it with the fluid, and I'll just kind of color that in a little bit. Okay, so this one has this amount in it. And we want to know at the bottom right here, what's the pressure comparison in each one? Well, the equation, of course, is pressure total is always going to be pressure of the atmosphere plus rho GH. Both of these, of course, are open to the atmosphere pushing down. So we'll label that just once here, pressure atmosphere. And we notice that the heights, okay, are the same for both. Okay, therefore the pressure at both of those locations are going to be the same. Okay, but what about the total gravity force acting on the left one versus the right one? Well, the right one obviously has a wider base to it, so there's, more weight to this right one because there's just simply more volume occupying all of this right here versus how much fluid is in this. So the total amount of gravity force on this one's going to be more than what it is here. But at the very bottom, the force per unit area is going to be the same. Okay, because rho GH is all you have to look for. As long as the heights are the same, no matter what shape the container is in, the pressure has to be the same. Remember, the pressure at each location at this place is all the same. At this place, it's all the same. At this place, it's all the same. Because, again, rho GH governs what the pressure is. Okay, now what about a question? I've got ice, okay, in a glass of water. When it melts, is there any change, okay, in the volume of the liquid total? And our answer is actually going to be no. And let's figure out why. Well, ice floats on water. And of course, the buoyancy force going upwards is balanced by force gravity going downwards. So those two forces have to equal each other. And we know that the buoyancy force is equal to the weight of the fluid, okay, displaced, okay, by the actual object that's floating there. Okay, so to get the weight of the fluid, okay, displaced, we're going to say the density of water, and we'll multiply that by the volume that's submerged, okay, underwater, and then we'll multiply that by G. That's going to equal the force of gravity of the ice, which is just simply the mass of the ice multiplied, okay, by G. Okay, so I'm going to cross off G's here. If I want to know what volume is submerged of the ice, because only the submerged displaces water, that's going to equal the mass of the ice, okay, divided by the density of water. Okay, so again, we've set force buoyancy equal to the force of gravity. Okay, so that's what we've got. Well, when this ice melts, all of it's going to become liquid. Okay, so the mass of the ice melted is going to have to equal the mass of the water that's liquid after it melts. So how do we figure out how much volume, okay, that has actually melted? Well, the volume of ice that actually melts has to equal the mass of the ice divided by the density of water. Okay, because mass is not changing here at all, is it? So the total mass of this ice, okay, has not changed at all. So whatever mass of ice we've got must equal mass of water. So if you substitute mass of water in here and divide it by the density of water, you've got to get the volume that actually melted. Well, since the volume submerged is got to equal the volume that melts, there will be no change in the height of the liquid here at all. It'll be identical. So that's how we show that when ice melts, the total volume doesn't change. So if you're worried about your water overflowing, if you've got some ice in there, it won't do it. So there you go. All right, what about another question to kind of simplify? Let's just say we've got water here. So this is H2O here. And we have a block, okay, floating in there. And let's say 50% of the block is above and 50% of the block is below. And we want to know something about the density, okay, of this block. Okay, well, that's pretty easy to do because we can do the volume of the object is to the volume submerged, okay, as the density of the water is to the density of the object. Okay, so that's a pretty easy ratio for us to look at. Okay, and let's figure out what that means. Okay, so let's go ahead and do that. So let's call the volume of the object just simply V naught. And the volume submerged is going to be 0.5 V naught equals the density of water. Let's just go density and put a W there. Okay, over the density of the object. Let's just do an O there. Okay, so then we can do a cross multiplication here. So I've got V naught times rho naught equals 0.5 V naught and rho of W. Okay, so what can we say then? Well, it looks to me like V naughts would cross off, and again, V naught being the volume of the object, and we end up with the density or rho of the object is going to then be half the density of water. So we can do a quick calculation here and think about that for a second. So we can, remember that it's inversely proportional to each other. So as long as we know what fraction of the object is submerged in water, we can get a quick calculation of its density relative to water. So what if 60% of the object is now submerged? Okay, well then I'll have a 0.6 on the bottom here, right? So that'll mean my density is 60% of the density of water. What if 80% is submerged? Well, then the density of the object is 80% of the density of water. So you kind of see how that pattern actually goes. And just as a quick follow-up for that question, what if I have an object, the same object, and we put it in 4 different fluids? And we want to kind of rank the order of the density of the fluids that are present. We'll go from least, okay, to greatest. All we have to do then is see what fraction of the object has now been, sunk in the water. So it looks like the object, okay, is sunk mostly in this fluid here. So we'll label that as number 1, meaning the least dense. Okay, so whatever fluid this is the least dense. And I look here, and it looks to me like more of the object is submerged here versus there. So this would get a number 2, meaning it's the next least dense. And then up here, I think we can clearly call that a 3. Okay, and then this one here is number 4. Most of the object is floating in this particular, whatever this, fluid here is. So this would show that the fluid that it's floating in is the most dense, and this one here would be the least dense. Okay, there's a quick review of some concepts. Good luck in your test tomorrow.